Starting. Okay, so if something will work incorrectly, then say me. I hope everything's okay. I moved something with screen with my do something with computer, but I hope you still see the screen and everything's okay. Okay, I hope I didn't do math, namely calculation number of lectures correctly. So today is lecture number 13, and today is already December. So I actually plan to deliver 3 lectures. So today, next weekend, in 2 weeks, of course, I will give you problems after last lectures, but I will. They all will be with stars. If somebody have to pass this course, then this problems are just auxiliary. I don't suppose that you have time to study this carefully, but of course I will encourage you. Okay, now let's move to the topic of today's lecture. And today we'll talk about representations, as we did last, I don't know, months. But I'll start with the concept that there is a class of representation which we did not discuss actually almost at all. We slightly touched them, but here I talk about highest weight representations. We mainly talked about finite dimensional representations, which are not highest weights, which have so-called loop highest weight, which for evaluation come from evaluation map from the highest weight representation of the finite, not affine quantum groups, but they're not a highest weight representation for affine quantum groups. Now we discuss another important class of representations, but before talk about quantum group, let me recall the corresponding notions for not quantum, for just affine the algebra. So if, as usual, G hat is affine the algebra, then we say that the sum vector zeta, okay, let's V is G hat representation. Then the vector zeta in V is a highest weight vector if generators E0, E or minus 1, ER on zeta. Okay, I'll write without dots. EI on zeta is equal to 0 from I 0 to R minus 1, and HI on zeta is equal to lambda I, again for I from lambda I zeta from 0 to R minus 1, where this lambda are some numbers, say complex. So this vector is annihilated by generators of the nilpotent subalgebra, and Kaplan part act by number. This representation G hat, okay, in principle we can talk about not G hat but G tilde, namely at differentiation. I will need it at some point, but maybe now. The first important class of so the highest weight representations, it means that the representation which has highest weight vector and which generates the whole representation. The first important class of the such models is a set of Fermat models. So, Fermat model. I denote it by V for Fermat and put here lambda. And put here K. I maybe denote it like this. Is free generated by U and minus okay. Is model generated by the following the highest weight vector with this highest weight. So the vector psi lambda k such that again all ei's on psi lambda k are zeros. And here I from 0 to r, hi from psi lambda k equal to lambda I psi lambda k from I from 1 to r, and k psi lambda k is equal to k small psi lambda k. So this is the action of the generator, and so this section is an important positive part. This is an action of Cartan. I choose generators such that I have h's which correspond to finite Lie algebra and also central k, central generator k, and for an important part, so u and minus, it acts on the Fermat model free. So more formal level, this definition can be stated that Fermat model V lambda k is universal enveloping of the G hat tensor over universal enveloping of the B hat to the model C lambda k. Means that for this algebra is generated by these elements, and it has a one-dimensional representation where O is x by 0, h by this number, k is by this number. And we take induced model. We induce from the one-dimensional representation the whole model, which is Fermat model. Another way to think about this Fermat model is the following: that V lambda k has a basis. F beta 1 power e1, F beta 2 power e2, blah, 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 F beta n power en applied to the highest vector psi lambda k, where these vectors F beta 1, F beta 2, and this is infinite collections form a basis. Can be any basis in n minus. Of course, all these models are infinite dimensional. Are there any questions? Okay, no questions. Do you hear me still?
Yes.
Yes. Okay. I'll speed up very soon, but I decided to start slowly. So I start from the definition of the Fermat model. Now, another class of representation which we will need is irreducible models. So I denote them by L capital. L lambda k is irreducible quotient of m lambda k. So it means that it has the highest weight vector, which is twice the same relations. But now universal of n minus acts not freely, but in principle, the section can have some kernel. And we take the quotient by certain submodel generated by this kernel. One more way to say that we take the quotient by certain singular vectors, which we have in the Fermat model. In this theory, in the representation theory of affine dimensional algebra, the most important class of the irreducible representations is the class of finite dimensional representations. There is no non-trivial affine dimensional highest weight representations in affine case. Instead of this class, we have the class of integrable models. So I can say it as a definition. And lambda k is integrable if for any I from 0 to R, L lambda k is sum, of course, infinite of finite dimensional. Before word sum, I'll write infinite. Of finite dimensional finite dimensional representations of the SL2 algebra, which correspond to this root I. SL2 generated by EI, FI, HI. This is so similar to the fine dimensional case, where the condition of representation fine dimensional means that highest weight should be integral. The similar condition holds in this case also. So maybe I put as a remark. Okay, or as a theorem, which neither proof neither use, theorem that if model is integrable, then its highest weight lambda should be dominant, and k should be integer, not non-negative, and k should be not greater than scalar product of lambda and theta. In this case, it will be equivalence. I said this, okay, so this is a general fact which is not very difficult to prove, and proof can be found in Katz's book. But again, I will not use this. I will not use the general notions of integrable representations. I will talk only about a very special class of integrable representations, a very special example. What I'm going to say today, it can be generalized and so on, but we restrict today to the case of SLN and actually SL2 mainly, and only on the representation of the level 1. Maybe the last word which I should say in general, so level is value of central generator K. Maybe. So it means that we will consider representation for K x by 1. Okay, now I'm going to talk about representation, level 1 representation of SL2. But before, are there any questions about about 2 pages which we have already covered? What we already said? Okay. Okay, I prepared some formulas because it was not to move faster when we will need them, but maybe before it the setting. So now our Lie algebra G is SL2. And okay, and its representations are labeled by so representations are labeled by the weight and non-negative integer number. In this case, the weight is again can be viewed as a number, and this condition can be viewed as a fact that this fact that, or maybe yes, here should be opposite inequality. Why not? So in the case that representations are labeled by some numbers, H and K, and integrable means that 0 less than equal to H less than equal to K, and H and K are both integers. Non-negative integers, of course, as we've seen from this. So we have two. We will consider so the first non-trivial case, first case where is K equal to 0, but in this case we have H also should equal to 0. So we have a representation with 0's highest weight, and clearly the only reducible representation is a trivial representation, trivial one-dimensional representation. Now we consider level 1 case. So we have two representations. One of them is L01 and another L11. From the point of view of affine algebra, these representations are fundamental. So this representation with highest weight pi 0, and this is with pi 1. So this is two fundamental. This is can be viewed as one more reason to consider this representation. We will now I'm going to give explicit construction of this representation, and this can be done using so-called the procedure which is called Bosonization or free field realization. I explained what I'm going to bosonize, if you want. Now so we start the procedure. So so more mathematical language means that we take some certain not quite simple algebra and then realize our representations using simple take representation of this simple algebra and then realize our image of the quantum affine algebra as a through this simple algebra. As subalgebra of this simple algebra. And this simple algebra is the Heisenberg algebra. Our Heisenberg algebra will have generators AR, where R is integer, and their relations will be like this. So if we take commutator of AR and AS, it will be some constant time delta function. So if R plus S is not zero, they compute. And so A0, for example, commutes with everything because the delta function can give something non-zero only if we take A0, which is definitely zero. So we add to this algebra one more generator, which we denote by Q hat. And commutation relations between A0 and Q hat is this. So we have Heisenberg algebra. These are relations. Let me write generated by AR, so Q hat and AR for R integer. And these are relations. The simplest representation which we have for this algebra is a Fock model. This model is generated by highest weight vector for this Heisenberg algebra. So this highest weight vector label this highest vector labeled by numbers by alpha, where alpha is a complex number. The word highest weight means the eigenvectors for A0 and they are vanished by AR for R greater than 0. And then the representation space is freely generated by A-1, A-2, and so on, negative A's. And they commute, so this is just the space of polynomials. This is space of polynomials of this infinite set of generators, A-1, A-2, and so on. This can be called Fermat model, but probably the most standard, definitely the most standard name for this model is the Fock model. This is a Fock model of the Heisenberg algebra, but I didn't define the action of Q. So this is a Fock model of the subalgebra of the algebra which I defined, so subalgebra generated by A's. This subalgebra is also called Heisenberg algebra. As operator, actually operator Q will not act anywhere in my notations, but it will. I will use its exponent. So I will introduce this operator in power beta Q formula, which acts from the Fock model with the momentum alpha to the Fock model with momentum alpha plus 2 beta, and this. Okay. I think I have problems with space, so I just move this to the next page. And then in final slides, I will decide how to organize material. So this operator, which I define, this operator E beta Q, it commutes with all AR for R not equal to 0, and it maps the highest weight vector beta Q alpha to the highest weight vector alpha plus 2 beta. And this 2 is quite natural. So if we take any vector, say psi, and act in power beta Q and then act by A0, then recommuting A0 with in power beta Q, we get to beta and plus initial term. So the eigenvalue, if A0 acts on psi with eigenvalue alpha, then A0 acts on this vector with eigenvalue alpha plus 2 beta. And since in power beta Q commutes with all AR for any R, then its only choice is to match highest weight vector alpha to the highest weight vector of this model, namely alpha plus 2 beta. This is a question of normalization, and I just assume that normalization is equal. Okay, so using all this stuff, we can state the theorem. So if we take, so there is an isomorphism of the vector space L01. This is isomorphic to direct sum of the Fock models F 2n for integers, and L11 is isomorphic f plus 1 minus 1, say, for integers with the action defined by so standard generators of the standard generators of the SL2 hat are so okay, maybe I should write it. Should draw this. Should write this above. So I assume that our algebra SL2 is generated by EHF. Or maybe, but instead of this, maybe I prefer to write now that it's generated by X plus, X minus, and yes, H. Then SL2 hat.
I'm sorry, is it only me or the screen is somehow bugged and it's like,
Ну да, у меня тоже трансляция запаздывает по сравнению со звуком.
Вот, например, сейчас нет никакой прямой суммы.
Да, нет теорем пока что.
I don't know what to do with this. Maybe yes, maybe there's a problem with internet here. Okay, let me stop. First of all, stop my video in order to speed up, and then probably I see what I'm sharing to you. So what I see is that now the theorem appears. The direct sum appears.
Да, да.
Okay. So first of all, let's wait where this theorem appears in full generality, and then I will do more explanation. It is interesting what we will see on the YouTube finally build. But probably the same.
А у меня вопрос, а вот почему, например, x плюс в бозонизации не зависит от q маленького? Там же оно должно быть все равно в коммутационных соотношениях.
Now we're talking about only affine algebra, not affine quantum group.
Хорошо.
This is still long preparation. Okay, now there is agreement with what is wrote in my iPad and what is written. Okay, maybe let me try to do the following. I change the way in which I share the screen. Maybe it will help. Okay. Okay, do you see my screen? I think yes, but
Yes.
yes. Okay. Please say me if you will see any significant difference between what I'm saying and what I'm writing. Stop. So now I'm writing that affine SL2 is generated by the modes of this x plus and x minus. And the action of the affine SL2 on this fork model is defined as follows. So the Heisenberg part, which is Hn, goes directly to An, which I defined above. And x pluses will act as a vertex operators. So x plus of w, which is usually in setting of the Affine algebra defined by the following, that is the sum of x plus n w minus n minus 1 goes to this. And for x minus, we have formula with a negative sign. So I'm just writing, so I put negative signs. Everywhere. So these are exponents. In principle, these sums are infinite, but if you take any vector, then first we act by operator which can annihilate this vector, so only finite number of terms appears here. Then here we have infinite sum, but again, if you want to act by certain mode, certain power of w, then only finite number of terms here can act. And this is now. This part is fine. If you first see formulas like this, of course, it takes some time for you to be prepared with. Maybe so if you see this at first time, it's of course better to start with these formulas and then talk about quantum groups. But since our subject is quantum groups, I will do the opposite. I will discuss a similar theorem for quantum groups with some details, but skip this. Okay, now in my plan, actually, so I plan to talk about more general construction which work for any GLN using fermions. But I think I already spent more than half of the lecture, or maybe like half of the lecture, and didn't talk about quantum group. It's bad, so I skip fermions. I put in my notes, and now I'll talk about quantum. So we want to have Q deformation of these formulas. Actually, we want something more, but first of all, this. It is convenient if you want to write down this. It is convenient to talk about to use a Drinford realization. This is one of the reasons why we. I mean, there are many reasons why we need Drinford realization. This is one of them. So there's a theorem I just copied from the lecture 5 with only one difference. So in lecture before, when I talked about Cartan generators and packed them, so here I used psi plus and psi minus. So I changed notation. So instead of psi plus minus, I use k plus minus because I will need letter psi for some other reasons. Up to this, this is just a theorem which I copied from the lecture 4. Okay. And now I want to write down similar formula, similar Bosnianization for the level 1 representation. As in this theorem, you see the Heisenberg, which we have in Affine SL2, just maps to the Heisenberg in, which I use for Bosnianization. This leads to a bit non-standard conventional normalization of the Heisenberg. So here we have 2. Usually, when people more standard normalization here should be 1 or minus 1. But
I'm sorry, this 2 is Cartan matrix, or
yes, no, this 2 is Cartan matrix, but how to say? If this is because I want to write, don't want to write number here. So
if we generalize, we will have not diagonal, like not just 2's, but 2's and minus 1's between the different indices.
If I want to keep this formula simple like this, then yes.
Mm-hmm.
or maybe, how to say? No. Here will be no. Here will be no. Cartan algebra just commutes. We will have, I think we will have Cartan matrix in the definition of the x plus and x minus, in the definition of the in Q equal 1 case, in the definition of Bosnianization. It depends how you're going to write them, but maybe in the standard way you don't have Cartan matrix here. No, I take back my words. You're right. In principle, this too is Cartan matrix. Yes. You're right. But I'm talking about SL2 just for simplicity. So first of all, if I want to write down Bosnianization, I have to take somewhere Heisenberg, and my Heisenberg will be the image of the Heisenberg on the affine from the Dirichlet realization. So the commutation level 1 means that k is equal to q. So this in this realization, this will be just q number r. So commutation relation between HR and HS is this. And sometimes I will denote this Heisenberg as A, meaning that it is the name of the Heisenberg in the image. And H is formally the generator in the quantum in the abstract algebra. So we have a map which maps H to A. Now we look to this relation, this and this. I just copy them, and here this 2r over r is a Q deformation of the 2 which we had in Cartan matrix. And here we again have Q deformation of the 2 which we had in Cartan matrix, but since we had K in the Dirichlet realization, then we get some Q in power minus R here. When we talk about fine dimensional representation, we can ignore all such K's and all such shifts. And, situation was simple. But now, situation like this, and this commutation relations leads us to the following. Uniquely determines this following part of the formula for x plus. Indeed, if we take commutator of this expression with AR, then here I put something about Q and A0, just ignore this, it commutes with AR. Here all A's again with positive, A's are positive. So okay, maybe I need some space. In order to have the space, I move all the stuff below. Okay. This is some preparations. So explanation, indeed. If we take commutator of AR with this exponent, so in this commutator, the only interesting term, the only term which which is not zero, is the commutator of AR and exponent over 1 over r a minus r wr. And this commutator, so when you think about this commutator as an analogy, you can think that we take commutator of the operator dx and the operator e in power some beta x. And this commutator is beta in power beta x. And this dx and in power beta x operator which commute by some number, say beta, as some number a. So here this corresponding operator is ar and a minus r. They commute to some number. So this commutator is equal to a number which is equal to. So this beta is a commutator of dx and beta x. And this lemma in the computation, we get commutator of AR and 1 over R A minus R WR times exponent. And this commutator is equal to what? Commutator of AR with A minus R is this over R, we divide over R. So, okay, so we get 2R over R WR times exponent. And this is exactly the same number which we should have here. Are there any questions? So this is the way how I wrote this part. And about this part, you can think that I just copied it from the previous case, but there is on the slide difference. Here I put +1 because in the QQ1, in the case of vertex algebras, when we define current, we usually put here -1 in order to stress that the conformal field theory language, this field has dimension 1. But now in Q-deformed case, there is no dimensions, there is no such shift, so we should multiply by W. Therefore, in the Q-deformed case, I get here +1, here also +1. This explanation for the formula for x plus. Similarly for x minus. So we know commutation relation of the Heisenberg algebra with x minus. I hope that here I copied to the correct formula for x minus. This formula is written here, and again we just substitute k is equal to q. So this is why we get here q in power r. This formula differs from the formula for x plus by what? Here by sign. Here we get q deformation of the 2, and this is q deformation of the -2. Yes, this is a misprint. Yes. So these numbers are just -2, and also due to the appearance of the k somewhere in the relations, we get q. We get q some numbers which you don't assume q goes to one limit. So we get q in power -r here, but q in power r here. And arguing like here, we get that formula that x minus is given by the following exponent. So where we are now? Did we construct the level 1 representation? Actually, no. Oh, I mean, in some sense, yes, but in some sense, no. It means that we wrote down formulas for x plus and x minus, and but it remains to show that all relations are satisfied. So here we used this relation in order to define what is the relation between Heisenberg which we will use, and these relations. But it remains to check two other sets of relations, this and this. And let me do at least one check, namely this one. I will use the following lemma. This is already prepared as a lemma. So if we have two operators, A and A dagger, such that the commutator is some number, say 1 or other number, then if I can permute their exponents with a price given by this number. So this is the commutator of these two operators. This lemma can be proven by just computation, which maybe I don't have time to do now. In principle, this can be not number, but any element which commute with both A and A dagger. But I think in all applications which in U, this is just number. And now I use this formula in order to commute x plus and x with x plus. So I take product x plus and x plus. X plus given by this x plus of w. So then if it is x plus of w, here should be w. And probably the same problem which we have with x minus. So I write this of z times this of w, and then I try to reorder terms in the following way. That first I will get operator which annihilate vacuum, so AR with a positive number, then A minus R, which creates something, and again do the similar ordering for the so-called zero mode. So first I want to have A0, and then I apply this shift operator in power Q. So after this recomputing, what do I get? I get so this first row is assumes that everything that I can just recompute. So write down x plus and x z and x plus of w, and then reorder terms as I want. So first annihilate AR with positive index, then A with negative index, then A0, then Q, as we had for one. So we have here W plus W. Here we have product Z in W. And here we get just 2 because this do not depend on Z in W. But when I reorder, I should pay some price, and this price is governed by this lemma. So, for example, in order to have this, I have to reorder. So, before I had the following: I had first z in power A0 plus 1, and then e in power Q. And if I reorder, then I get them. Okay, with opposite order, but I have to write exponent of the commutator of their logarithm, and this is written here. Maybe not to here. I wrote here, so take the logarithm of this. I wrote A0, not A0 plus 1, because 1, of course, commutes with Q. So this reordering is this. Similar origin is of this term. I have to reorder the this part of x plus of z with this part of x plus of w. And therefore, I have exponent commutator of these two terms. Okay. What is in first order? I is usually denoted as a normal order. So this is just a notation. So this is just a notation for the first row. This is notation for the first row. The meaning of this notation, so we take x plus of z and plus of w, and then order terms such that first, ignoring the problems with that commuting can leave there's some price to pay when we commute. So first, and the rule is that as used everywhere, a with positive indexes first and a with negative indexes. So this is the first row, and for the second row, what do we have? So this is z squared, because commutator of a0 of q is 2. This is, I forgot to write it in q deformed case, but for q equal 1 case, it's and in this exponent, what do we get? So I put all these numbers, q in power minus r, and then wrote commutator for r and a minus r. And this is the product two q numbers, 2r and r over r, w over z over r. Okay, then I repeat this term. And here we can perform a lot of cancellations. So r is constant with r. 2r is what is it? Q in power 2r minus q in power minus 2r. And minus r is q in power r minus q in power minus r. So after the cancellation, we get something like q in power r plus q in power minus r. And after this multiplication, we get this numerator. And minus r of the denominator, this minus remains. Okay. And this is exponent of the actual logarithm of something using the standard formula for the logarithm, and get this. So product of x plus of z and x plus of w is equal to this, and hence if we take this term x plus of z, x plus of w times the function plus x plus of w plus times the functions. So this is just the first row of the relation. Then we can rewrite this term as a normal ordering times now the product of three factors. So one factor we already had, and two factors come from this reordering. And here we do the same and reordered normal ordered product of x plus of z, x plus of w, normal ordered product of x plus of w and x plus of z are the same. So they are appeared here, and here we get the sum of three functions. And it remains to note that this sum is 0. Due to the z minus w and w, so this product is equal to, and these two products are equal. Just can move this q squared from one bracket to another, but due to z minus w minus z here, we get 0. So here we check the relations for x plus of I will not check any other relation. I actually plan to state it as a problem, but let me summarize what we already done as a theorem. So and the theorem will be the same as for q equal 1 case. So we can take direct sum of, so we take the Heisenberg algebra. With generators q hat and ar, r is z, with relations that commutator of ar as is equal to, as we had above, to r over r dot r plus s, and commutator of a0 q, or I can write it generally, commutator of ar q is equal to 2 delta r. So it is 0 if r is not equal to 0. Then if we take the seamless direct sum, sums of f to n prime is integer, and the direct sum f to n minus 1 are representations of affine quantum group with the highest weight, with x plus of z, x minus of z, hr as above. So what I tried to explain, at least I tried to explain that on this sum we have an action of the UQSL2 hat. So we defined operator x plus x minus such that these relations are satisfied. I checked this relation. Of course, it is easy to believe that this relation is very similar, and actually it remains to check this. It can be done, and maybe this will be a problem. Therefore, this basically we construct the action of the UQSL2. If you want to state that this integrable representation, we have to check a bit more. We have to check that that highest weight vector has we indeed has highest weight vector, that its highest weight is equal to what is should equal, and the representation is integral to it means that some singular vectors vanish. But since the representations are for highest weight representations for QSL2 have the same size as the representation of the ordinary SL2, this is straightforward. Okay.
Значит, можно указывать не только SL2, отвечающие корням, а простым корням, а SL2, отвечающие другим корням, и тоже, если у них раскладывается представление, оно будет тоже очень ясно. Тут можно такое
for quantum groups, this question, what is SL2, corresponding to not simple root. What is In principle, yes, we can use automorphisms, and this sense, yes, I think everything remains the same. Yes, if you define as SL2, you just using this automorphism, the composition will remain the same. Yes, yes. Okay. Are there any other questions? Do you still hear me?
Yeah.
Okay. So actually, so you see, I skipped some checks in this case, and to be very honest, I skipped some definitions. I didn't define you what is L01 for the Q-deformed for quantum groups, but the definition is the same. This is all because I really want to talk about additional objects, which are vertex operators. These operators are important even for Q=1 case. So as a digression, if you want, so okay, I don't know where I will put it in my final notes. So first of all, what do I mean by vertex operators? So if I have I have the finite dimensional representation of a fine quantum group, which I denote by V. So V of U will be C2 of U is evaluation representation. And vertex operators are defined as the intertwiners of the following form. So I defined from the very beginning 4 vertex operators. They're very close, but the first with the difference is quite simple. So difference between phi and psi is that from one case we multiply by this evaluation on the right, and to another case we multiply on the left. For Q=1 case, this is the same. So phi is equal to psi, but for Q-deformed case, this additional phenomena which we get due to non-commutativity of the coproduct. And difference between phi and 5 star is multiplied on the image or on the pre-image. Since for SL2, V and V star are isomorphic up to some shift of the evaluation parameter. So for SL2, phi and 5 star are actually the same vertex operators. So it is sufficient to consider one of them. But for SLN, it will be more interesting. I didn't motivate it from Q=1 case, so I put a remark after the definition. For Q=1, this
А можно еще раз, а как устроено отображение?
This I put only. I just said that these are intertwiner operators. Such intertwiner operators exist up to the constant, but I mean this is a theorem which we will actually prove. But I didn't define this map explicitly, and this is actually topic of the remaining part of the lecture. Write down the formulas for these operators. But just now I said that these are just intertwiner operators. if you think about these spaces as a sum infinite using same infinite construction, then this operator phi is a wedge with some k. So we had this operator phi up to actually last lecture using same infinite construction. Or maybe not but this. Let me think. Okay, we had one of these operators in last lecture using same infinite construction. But I'm not sure which one. And actually, I have some doubts about my nomenclature about these operators. No, maybe everything's okay. 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 So for QQ1, we can use Bosonization, and we can write formulas for this operator. So phi of u is equal to psi of u is equal to because this space is two-dimensional, we have two formulas, and formulas will be given by will be the same as we had for x plus and x minus. With one simple difference. That we should put 2 everywhere. So this is some sort of a square root of the generators E and F. And you see these operators, they map from one integral representation to another one. So in terms of this decomposition, here we have summation of an integer zero mode, and here summation of a over even, here with summation of the odd. So this vertex operators shift zero mode by one. Of course, this just follows from the commutation relations. So this on this space V, Q deformed setting K acts by numbers Q and Q inverse. Or in the Q1 conformal setting, H0 acts by numbers 1 and -1. And here H0 acts by even numbers, here by odd. So everything agrees. So this is this operator which intertwine two different integrable implementations which we construct. And x plus and x minus are some sort of the square root of square of these operators. I didn't talk about Fermi new constructions, but just for those who knows, so I write that these operators are fermions. Up to some something which is called dressing, which is responsible to difference between GLN and SN.
А зависимость от U, она сидит в 0?
Okay, maybe I put here W in order it will be simpler for me now. W appears everywhere here. Actually, there are two versions of this operators. One can consider this here U, which is W here, as a complex number or as a formal parameter. So take formal evaluation representations, and these formulas work in both ways.
Фи должны включаться на что-то типа матрицы.
No, how to say? Actual answer is no. So there is no matrix which will permit phi to psi.
А почему нельзя взять композицию фи с R-матрицы?
I think it will not act on this representation. I said, okay, I think this will not work. So just using so phi psi are object of, they're just different objects. Okay, so I have not much time left, so I will now show you some formulas using my preparations, which I don't put to the final file just to show. So first, I want to say state you the following: that there I defined the operators as intertwiners, but I actually didn't specify what kind of coproduct we use. And there are actually two choices here. You can either use Drinfeld coproduct, or which is somehow useful for new Drinfeld realization, or you can use standard Drinfeld-Jimbo coproduct. And the answers will be different, and which I will now going to show you. So first of all, for Drinfeld coproduct. So I put letter D here, so and coproduct is Drinfeld. As before, it is convenient to decompose our operator into two parts. So for somehow technical reasons, I start from psi star, and so psi star acts in this direction. And this space is two-dimensional, has a basis, say psi plus and psi minus. And I define that psi star d on psi plus standard zeta as a psi star d plus, and similar for minus. So this is the same as we had here. We had here two formulas, and these are formulas for phi plus and phi minus. Now I put this as the definition. Okay, now delta d, this is the formulas for the coproduct, Drinfeld coproduct, which we had somewhere, and so this is a working file, so I always have typos, but here we'll have more typos than usual. The coproduct of k plus is equal to k plus times k plus, k minus equal to k minus to k minus. And in terms of the Heisenberg, the coproduct looks like this. So k plus is like a group type element, and h is like the algebra element. Now the action of this h on the two-dimensional representation is like this. So we have this two-dimensional representation is a not highest weight representation, is L weight representation. So it has it in the standard basis is eigenbasis for the k plus and the same for k minus. These functions are called more or less called L weights when we talked about fine dimensional representations. And if you know how k plus and k minus act on this vector, we can take the logarithm and write down formulas for the Heisenberg. here they are. I quite often move from U to A. This is a convention which we used, which I don't know, at least I used several times in my notes. But for two-dimensional presentations, with some A is somehow better parameter. Okay, now after all these preparations, we can write down commutation relation between psi and H. So we have intertwiner property. So we can take any vector zeta, apply to it psi star, take zeta times psi plus, apply psi star, and then apply Heisenberg. Then from the one point of view, this is just psi plus, and then apply Heisenberg. On the other hand, using intertwining property, this can be written like this. And this can be written like this. Now, here we have two terms. One term is just action of is this one. So we have on the first component we have just psi plus. So this is psi plus of by our definition is psi plus, and this H acts on zeta. So we get this term. And for the second term station, a bit more interesting. So this k in power r acts on zeta. Zeta is the element of the level 1 representation, so we get q in power r. This hr acts on this psi plus. This is why I prepared the formula for the action. We get this number, which I put here. So we can just act by this element and obtain the psi plus acting on the original vector zeta. So as a result, this can be viewed as a commutation relation between the Heisenberg HR and psi plus. Therefore, similarly we have for minus, and therefore for psi plus is just exponent. We get formula for exponent. And this formula is similar for the formula which we had for the x plus and x minus, but here we have not just r. We have this 2. We should divide over 2 our function here, but somehow this 2 comes into the q number. So now it's not the square root of the function which we had. Up to this instance. I don't know. And if you want, here are the formulas for phi plus and phi minus. And there also will be some exponent. I didn't write formula for psi star minus. I wrote formula for phi because I just prefer for some reason. I don't know for which reason. So what is different between them? So both of them are just, in both of them we have in denominator just number 2r. And they, of course, they differ by sign. So one, because they differ by direction. And they differ by some powers of q. So here argument is u, here u in q minus 2, and so on. So the thing to take away that for Drinfeld-K product, everything is given just by exponents. I didn't prove because I computed the simplest commutation relation with H. And this commutation relation completely determine our vertex separators. What remains to show that these formulas intertwine action of the x plus and x minus and stuff like this. But this is possible, and I think I left it as a problem. Any questions? Okay, if no, then okay, let me look to the time. Is it true that I should stop now? Yes, I should. So I will not show you all this computation which I prepared. I just try to some results. So for Drinfeld Jimbo. Just what does them? Yes. So phi plus is the same. I put plus up below. Phi plus is actually the same as for Drinfeld. Phi minus is not exponent. So there are two formulas for phi minus, and one of them is could be like this. It's the integral over something of a certain contour over some exponent. And even this formula requires some work, some calculation, much more non-trivial, because we have a completely different product. This is one. Second, so this if you want this some sort of disadvantage of the Drinfeld Jimbo of the Drinfeld Jimbo vertex separators. Now, advantage is that, okay, so they're more difficult, so an advantage they're more interesting. And this is written their commutation relation. So if I write phi1 of u1, okay, 5 u1 phi of u2, then this is equal to R matrix of and this and because if we have this map from L to L times C2 of U1, so one of these maps is given by so in both left and right sides are maps from the integrable model times a tensor product of two of two relation representations. And these two elements and these two representations are isomorphic using now we can take just finite dimensional matrix. I mean, so I'm about your question about can we use a matrix formally there? I'm still not completely sure because we have problems with normalization and stuff like this. But here there is no problem because we use finite dimensional matrix, just 4 by for SL2, just 4 by 4 matrix, which we wrote several times during this lecture. So obtain something which, and the fact that the commutation relation is given by a matrix, this cannot be achieved just by exponents. This is one of the disadvantage of the fact that we have difficult formula for phi minus. And okay, there are other commutation relations between phi and psi and so on. But just to say just the last word, that matrix elements is of phi satisfy QKZ equations. And again, phi is a different phi. It's a phi which is constructed from the Greenfield-Jimpa coupling. Okay, I'm out of time, so I stop. Okay, if there's no questions, I stop recording.